Hello, my name is Alexandra Loaiza. I am a PhD candidate in the School of Materials Engineering, and I'm going to present a regression analysis on concrete. So let's get started. So concrete is an important material used in construction to build bridges, buildings, roads, etc. This material hardens in a hydraulic reaction with water. And one of the most important properties of concrete is the capacity to withstand high loads. This property is called compressive strength, and it requires at least 24 megapascal to be functionally accepted. So the basic ingredients of concrete are cement, water, and coarse aggregate and fine aggregates. Cement acts as a binder for the aggregates that, together with water, form a slurry easy to pour and moldable. The other ingredients are added to the concrete to improve some properties like compressive strength or workability, among other properties. In this project, a linear regression will be developed to predict compressive strength. The data contains 8 variables, which are cement, blast furnace, fly ash, water, superplasticizer, coarse aggregate, fine aggregate, and age. To study variables behavior, we have a box plot and a scatter plot. Judging by the box plot, we can identify some outliers, and by scatter plot, we can identify clearly any multicollinearity if there is some. This data can be found in this link in case you are interested. This data also has been previously modeled by artificial neural networking. My research question in this case is to find a model to predict compressive strength. So, in order to find a good model to predict compressive strength, a first-order model is built. By looking at the summary and ANOVA tables, p-values of x5, x6, and x7 indicate that these predictors may not have a linear impact on the response variable. Residuals plot and normality indicate several violations. In the next slides, we will see what are these violations. When we want to look for violation of assumptions, Brown-Forsyth tests indicate that there is no violation on constant variance, as we can judge by looking at the p-value, which is larger than 0.05, and no violation on normality according to Shapiro test. However, the residual plots against each explanatory variable and fitted value presented a strong indication of violation constant variance on X5 and X8 predictors. Scale location also indicates violation of equal variance, and residual versus leverage plot confirms heteroscedasticity and shows some potential influential points. When applying best-out function, we want to select a model that do a better job on prediction new data, as that is the research question that we are solving here. AACP and CP are the best criteria to solve our research question. According to that, we should pick Model 6. However, Model 6 is leaving out X6 and X7 predictors. As I was saying in the introduction, these predictors correspond to aggregates, which are basic ingredients for concrete. Without these basic components, concrete will not be concrete. The added variable plots confirms the findings in the best subset, showing for X6 and X7 flat patterns, indicating not much added value to the model. Influence plot shows some possible outliers and influential points. We have 3 outliers, 21, 33, and 324, and no moderate and no major influential points. Here we can see the matrix with points that may cause a large impact on to large DF betas, judging by DF fits 21, 33, 199 at 324 are influential points, and BIF table returns numbers less than 10, which means that no serious multicollinearity problem is detected. So let's try some remedial measures. A second-order model was built to find if it fits better the data than a first-order model. As there are too many predictors in the second-order model, I made a partial F-test to determine if some predictors can be eliminated. According to the F-test, the predictors tested in the hypothesis test, beta 11, beta 44, beta 66, beta 12, beta 45, beta 56 equals 0. So we do not reject null hypothesis. So it means these predictors equals to 0. We can then eliminate them. Then this second order model was tested without those predictors. Again, X7 seems not to have major impact, and also X23, X34, and X78. To transform Y, a box cos was performed giving a lambda of 0.63. Then the transformation suggested is a square of Y. In this case, X5 seems not to have major impact on response Y, judging by the p-values. Weighted least square was also performed. Again, X6 and X7 seems not to have major impact on response Y. And comparing residual plots, we can see that Y transformation and weighted least square make a better job on the residual variance. Normality plots show that Y transformation shows a normality on the residuals. Influential plots show that Y transformation has less influential points than the original model and the weighted least square model. According to lack of fit test for the second order model, there is a lack of fit. However, the k-fold cross-validation result indicates that the second order model is a better model than the first one. When comparing the unweighted model with the weighted model for the first 4 predictors, it seems that the unweighted model is more conservative to make predictions than the weighted least square model. In blue are the unweighted least square, and in red the weighted least square model for predictors X1, X2, X3, and X4. Neural network shows high accuracy to predict comprehensive strengths. However, for simplicity, regression models are widely accepted. So, thank you so much. I appreciate your attention, and comments or questions are welcome.